Section 2 deals with electrolytes, which I mentioned a moment ago, and I'm just going to go ahead and move right along. So electrolytes are things that completely dissociate or break down into individual ions in solution. Ions, that is, have a charge. And then it turns out that it's strong enough that you can get the solution to conduct current. Now, having said that, I do want to point out here that it's not the solution that is lighting up the light bulb here. This is a wire that is plugged into an outlet. For there to be a complete circuit, there has to be a closed loop. Well, what we have here is a gap, but the solution allows the water to fill in that gap. And then it does turn out that your individual charged pieces in the solution are attracted to each individual electrode that's in there. You can actually use that for some interesting chemical reactions in a field called electrochemistry, which unfortunately we won't get to here in this course. Weak electrolytes then only slightly dissociate in water, and much of it remains undissociated. And so then we have some that does dissociate, but then some that recombines and reforms the original. And so you'll notice here we do have some individual particles in solution. And it actually turns out that eventually this one here will break down into the hydrogen and the fluoride there. However, it's also going to turn out that those two are going to recombine, or of course other pieces like them are going to recombine. The amount that are broken down in there stays the same at all times, but you always have some pieces breaking down and some pieces recombining there in the solution such that the balance is the same. And you'll notice here that the light bulb does not light up as brightly. It is less conductive because there's fewer pieces. And then there are non-electrolytes, and non-electrolytes dissolve as whole molecules. That is, they start as one thing and they don't break down into smaller pieces when they dissolve. So they do dissolve here, but because they don't produce ions, then they don't conduct electricity. Now, I do want to back up here for just a moment and point out that a strong electrolyte is something that breaks down. That doesn't tell us anything about how much is dissolved. And we have a whole section later dealing with concentration, how much stuff is dissolved. We touch on it briefly here in this section. You can have very little of a strong electrolyte dissolved. It is not very conductive when that happens. If you have a lot of it in there, then you have a high concentration and a strong electrolyte. It's going to conduct electricity. Here, even when we have a high concentration, it still does not conduct electricity well because it doesn't break down completely. But don't confuse strength with concentration. They are different from one another. This here is just a summary of some of that, and I encourage you to take a moment and look at it, but I'm going to move right on along to some of the examples here. So this one here asks us to write the reaction equation. Well, it turns out that when you have a strong electrolyte, it's going to break down into its individual pieces in solution. And so that calcium ions and chloride ions. Now, I do want to point out here that the chlorine, this thing is made up of a calcium and two chlorines. When it breaks down, each piece breaks apart individually, and so you end up with two separate chlorines there, not as this one has here, Cl2. That is not what happens. Instead, we get this with individual ions floating around there in solution. This one here breaks down as well. However, notice we have phosphate, which is one of those polyatomic ions from earlier in the course. And so then we have 3 potassium ions because that 3 subscript becomes a coefficient here. However, that doesn't happen on the phosphate because the phosphate is the ion. The PO4 is a group of atoms working together as an individual ion. So those polyatomic ions that you thought you were done with and possibly have forgotten, here they come back up again. And so if you don't remember them, don't know them, you may want to go back and review them. Having said that, as a friendly reminder, when you have something like, and let's just choose another one, if the parentheses are there, you know it's got to be a polyatomic ion. If, on the other hand, we don't have the parentheses there, you know that you've got to have a polyatomic ion when there are 3 or more pieces, and usually it's the thing that's next to the oxygen that is your polyatomic ion. So those polyatomic ions don't break down when they go through a chemical reaction usually, and they definitely don't break down when they dissolve in solution. This next one here asks us which one produces a strong electrolyte in water. Well, we know a strong electrolyte is going to have charged pieces, so that is this one here. These two, it turns out, even though they don't ask us, are non-electrolytes. This one here, it turns out, would be a weak, although you have no way of identifying that really right now, and you can make an argument that it's actually reacting with the water instead. Here they ask us to write out the reaction equations from scratch, but we can handle this because we just did the others as if they were from scratch and then pick choices from what was there. But we're told here this is strong electrolyte, so it's going to completely break down. Once again, we have a polyatomic ion in here, the chromate ion, and so it's going to stay together, and that is our reaction equation there. Technically speaking, they like to have the water over there. It's not really necessary. It's kind of assumed if you have aqueous over here that there must have been something dissolving it, and aqueous means dissolved, usually in water, so we don't have to worry about that. In fact, you can hear the agua in there if you're familiar with Spanish or other romantic languages. I know they're all similar. Anyway, here we have hydrogen phosphate, also known as phosphoric acid, and it is only weakly soluble, and so we're going to have the double arrow there, and it's going to form hydrogen ions. And once again, there's a polyatomic ion. In fact, we've already seen the phosphate polyatomic ion in solution. This one here, in part because it's a hydrocarbon and you kind of just can recognize it from that. Hydrocarbons are not going to dissociate. Beyond that, this has no way it's ionic. It's just way too many pieces to be something that's ionically bonded. And beyond that, they don't tell us anything about it being an electrolyte, and so you can pretty much assume that it's a non-electrolyte. And so then we have C12H22O11 solid dissolving to give us C12H22O11 aqueous. So soluble, but doesn't dissociate and give us charges in solution. One thing that kind of makes solutions a little annoying is that, much like in the gas laws, there's so many different ways to measure gas pressure. Here in solutions, there's so many different ways to measure how much stuff is dissolved, or what's called the concentration. One way to do that is something called equivalence, which is used a decent amount in the medical field, but it's the amount of electrolyte that gives you 1 mole of charge. And so that could be positive or negative charge. And the amount of positive is always equal to the amount of negative. And again, here it's usually used in IV solutions. However, they'll measure in milliequivalents. And of course, just like previously, it's 1,000 milliequivalents to give us an equivalent. Now, technically, both of these are per liter, so it kind of gives us another equality here that we have 1 liter as well there. The other way you could write that as per liter for each of these, but really, if we're showing equalities, it's these 3 equalities, which we can then use for a large handful of conversion factors, as we'll see in upcoming examples. But for example, let's say there's an IV solution here that is sodium chloride and potassium chloride, and those are your most common IV solutions. Even if you're putting medicine in there, most of it is fluids, and they're fluids. If we just put water in there into your blood, you'd be diluting your blood. Well, since your blood and your body fluids are mostly a salt water of some sort, it helps to add that in there. The potassium tends to be used if your body is short on potassium, or for people who have certain heart conditions that make them sensitive to sodium, we can give them a little bit more of the potassium solution. But if there are 25 milliequivalents per liter of sodium and 4 milliequivalents of the potassium, then the total positive milliequivalents, we just add those two together and we get 29 milliequivalents per liter. And since the two of them have to be equal, then the chloride, if that's the only negative ion, then is 29 milliequivalents. Now, something that example doesn't show that we get to see here on the chart is that if we have a 2+ charge, then we get 2 equivalents. A 3+ charge, or minus charge, we then get 3 equivalents. And so it's measuring not the number of pieces, but the charges there, that a calcium is 1 piece, a calcium ion is 1 piece, but it gives us 2 positive charges. And so then that 2 positive is 2 equivalents. Here then we have a certain amount of calcium that is in the blood, and we want to know how many moles of calcium there are. So we're going to start with that 0.5 liters of blood, and using blood as a chemical label just amuses me for some reason. But here we have the 8.8 milli equivalents of calcium in 1 liter of blood. And so our liters are going to cancel out there. Well, here we're at milli equivalents, and so I can say that there are 1,000 milli equivalents in 1 equivalent. In that calcium, because it's got a 2 plus charge, there are 2 equivalents in 1 mole of calcium. And so then we end up with 0.0022 2 sig figs moles of calcium 2 plus ions. The chloride, if that's the only other ion present, then it asks for what's its concentration in milli equivalents. Well, the nice thing is the positive charge has to equal the negative charge, and so we also have 8 milli equivalents per liter. Now, you may say, wait a second, those are different charges, and you'd be correct, but that's only going to affect our molarity out there in the end, not our equivalents. The equivalents have to be equal to one another. And in fact, calculating it out for chloride here would be the same, except we'd have just 1 equivalent there. And so it turns out that it would be 0.0044 moles of chloride ion, even though they don't ask us to solve for that. I'll point out that if you're following with the PowerPoint version, that this one just had flat out the wrong title on it originally. I fixed it here, but this is just a simplified set of solubility rules, and basically tells you that if we have a positive ion, and it turns out here that we're looking at 1 plus ions, or more specifically the alkalis, metals, and the ammonium there. Also turns out hydrogen would be included in that list, though you can make an argument that the hydrogen is reacting with the water and not actually dissolving. They are going to be soluble. Most of your -1 ions are going to be soluble, although there are some exceptions when we get into the halogens. When they are combined with certain heavy metals. It also turns out that fluoride is so electronegative that it never wants to let go of what it's holding on to, and so fluoride ions are insoluble. And sulfate is also insoluble except when combined with certain heavy metals. It turns out silver should be on this list as well, and you'll notice that silver, lead, and mercury-1 are all on this list. There are other heavy metals that also are insoluble with sulfate, but these are your common ones. And compounds that don't contain at least one of these are usually insoluble. That is, one of these soluble ones here, ignoring the exceptions, are usually insoluble. If you're using my periodic table, I have a lot more solubility rules on mine than that, and if you're with me live, I'll show you how to read that one. For those of you who are virtual, I'll try to remember to post a video for how to do it, but you can either use that and learn how to read it, or you can just memorize this list. I will point out that part of why I call this the alkali metals and these other things, the halogens and these other things, is to make it so there's fewer things to memorize, rather than having to memorize each individual ion that's soluble. I will also point out that when I've made students memorize the list, and heck, even if I don't make you memorize it, labs usually you just eventually pick this up, that all nitrates, all acetates are soluble, most halogens are soluble, and all alkalis are soluble, along with a couple other positively charged things. When I made students memorize it, like I said, I'd make them learn that all alkali metals, all nitrates, and most halogens, and that was usually enough to get them through anything they needed. Now, despite introducing solubility rules, they don't actually give us any practice over solubility rules here in this topic. But for our last slide here, we're just asked a few more equivalent questions. So 1 mole of iron 3 plus, there would be 3 equivalents here. 2.5 moles of 2 minus, well, that's 2.5 moles, and we've got the 2 there for the negative charge, so that's going to give us 5 equivalents. And this one here tells us that there's 34 milliequivalents per liter of the sodium there, so it has to be equal for the chloride ion there. And that finishes section 2.